Welcome to the Deep Dive. Today, we're tackling something absolutely foundational in the world of digital information, relational databases.
Mm-hmm. The bedrock.
Exactly. Think of this as your ultimate study guide. We're going to thoroughly unpack the core concepts. We've got our source material here, excerpts from a DBMS PDF by Sharika TR.
Right.
And our mission basically is to leave no stone unturned in understanding relational databases. So what are they at their heart? How are they built? And how do we manage all that crucial data inside? Let's get started.
Absolutely. So to begin, our source tells us that a relational database organizes information as a collection of relations.
Okay, relations. What does that mean in plain English?
It's essentially a table. Think of a spreadsheet,
Right, like Excel.
Exactly.
Hmm?
And every single row in that table, that's a collection of related pieces of information, a single fact, if you will.
A fact about something.
Precisely. And to really nail this, like for a test, we need the terminology down. The entire table is the relation.
Okay.
Each individual row is a tuple.
Tuple. Got it.
And the heading of each column, that's an attribute.
Relation, tuple, attribute.
Yeah.
Okay, so starting to build the picture.
Yeah. And our source gives a really clear example. An employee table
Okay.
with attributes like employee number, name, address, mobile number, age, and salary.
Standard stuff.
Right. Now imagine a few rows filled in, maybe employee 101, RAM, lives as XYZ, phone number 9898, whatever. 20 years old, earns 10,000.
Okay, that's one tuple.
There's one tuple. Gives us all the details for one specific employee. And the source emphasizes the relation this table. It's a two-dimensional structure.
Rows and columns.
Exactly. Fixed columns, the attributes, but you can have, basically any number of rows, each representing a different entity, a different employee in this case.
Okay, clear structure. So now that we have that table image, let's break down the fundamental building blocks. What makes up a relational database?
Right. According to our material, there are 5 key components we need to know. Domains, tuples, columns, keys, and the relations themselves, the tables.
5 core pieces. Let's tackle them one by one, starting with domains.
Domains, yes. Our source explains a domain has a name, a data type, and maybe a format. But fundamentally, a domain is the set of all possible atomic values for a specific attribute.
Atomic, meaning?
Indivisible. At least as far as the database model is concerned, each value is a single unit. Think of it like defining the allowed ingredients for that column.
Okay, like only numbers or only dates or specific text formats.
Exactly. A domain has that logical definition too. The source uses USA phone numbers as an example.
Ah, so not just any numbers, but specifically valid phone numbers.
Precisely. It's the set of all valid 10-digit US phone numbers. And importantly, it might also imply a specific data type or format, like maybe they must follow the DDD format.
Right, or dates needing to be YYYY
Exactly, or MMDDYYYYY, whatever is defined. The domain basically sets the rules for what kind of data is allowed in a particular column.
Got it, sets the boundaries. Okay, component 2, tuples. We know these are rows.
Right. The source reminds us a tuple is an ordered set of values. It's that horizontal slice across the table.
The whole row's data.
Yeah, describing a single thing, an entity, maybe a relationship between things, or just an object. It's also called a record sometimes.
Record, tuple, row, same idea.
Pretty much. And here's a key point to remember. Really lock this in. Every single value inside a tuple must come from the specific domain defined for that column.
Ah, so the value in the age column has to be a number allowed by the age domain.
Exactly. Our source gives another example. A tuple like Kumar, Singh, 5257 store, 2230001, 98898989899 from a customer relation.
Okay.
You can see how each piece, the names, the address, zip code, phone number maps to an attribute in the customer table. And Kumar has to be valid according to the name domain. 223001 has to be valid for the zip code domain, and so on.
Makes perfect sense. Keeps the data valid.
Okay, then we have columns.
Columns, also called attributes or sometimes fields.
A single cell in the table, where a row and column meet, holds one specific field value or attribute value, just one piece of data.
Like in our employee table, the cell where Ram's row meets the age column holds the value 20.
Exactly. The source used the example of a person entity having attributes like eye color or height. The columns define what specific characteristics we're recording.
Okay. Defines the structure vertically. And the fourth component, keys.
Keys, yes. This is a really crucial concept to grasp. A key, according to our source, is a data item, or maybe a set of data items.
Could be more than one column.
Could be. And its vital property is that it uniquely identifies each and every row in the table.
The unique identifier, like a student ID number.
Exactly. That's how we guarantee we can tell one tuple apart from all the others. No two rows can have the same key value. The text also mentions something called artificial or surrogate keys.
What are those?
Sometimes, the system itself just assigns a unique number to each row automatically, like a row ID, maybe just 1, 2, 3, and so on. These aren't part of the real data, but they serve that crucial unique identification purpose.
Ah, like an internal tracking number.
Yeah.
Okay. So keys ensure uniqueness. And the last component,
Is the relations themselves, the tables we've been talking about all along.
right, bring it full circle.
Yeah. The source describes them in a few ways.
Mhm.
A collection of values in a table, a set of rows, or even a set of columns. But the main idea is that two-dimensional structure of rows and columns. Each row is a fact about some real-world thing.
An entity or a relationship.
Right. And importantly, each row has that unique identifier we just talked about, the key.
Okay, so domains, tuples, columns, keys, relations. Those are the 5 pillars.
That's a good way to put it. Now that we have those components, let's look at the schema and the state of a relation.
Schema and state. Right,
Yeah.
schema first.
Schema. Our source says this is basically the blueprint, the design of how the data is organized. Formally, it's written like R, A1, A2, ARN.
R is the table name.
R is relation name, yeah, the table name. And A1 through AN are the attributes, the column headers.
Okay.
And crucially, each attribute AI has a domain, DOM AI, defining all its possible valid values. So the schema describes the relation's structure. Like the domain for custod might be defined as only 6-digit numbers.
So schema describes structure definition, like the architectural plan.
Exactly. And related to that is the degree of a relation.
Agree.
Simple concept. It's just the number of attributes in the relation.
Right.
How many columns it has.
So our student table with ID, name, age, department number, that has a degree of 4.
Correct. 4 attributes, degree 4. We can even write it out, including the data types like student I.integer, name.string, age.integer, department no.integer. Makes the schema even clearer.
Okay. Schema defines structure, degree counts columns. What about state?
Right, the relation state. The source gets a bit more technical here. It defines it as a subset of the Cartesian product of the domains of its attributes.
Whoa, Cartesian product. Okay, let's unpack that.
Yeah, sounds fancy, but the idea is straightforward. Remember, each domain contains all possible values for an attribute.
Right. Like all valid customer names up to 25 characters for the custom domain.
Okay, the Cartesian product is just all possible combinations you could create by picking one value from each attribute's domain.
So if one attribute domain has 2 values, 0, 1, and another has 3 values, A, B, C,
then the Cartesian product is all pairings, 0A, 0B, 0C, 1A, 1B, 1C. That's 2 times 3 equals 6 possible combinations.
got it. All theoretical possibilities.
Exactly. Now, the relation state is the actual set of those combinations that currently exist in the table at a specific moment in time. It's the actual data in the table right now.
So it's a subset of that big Cartesian product list.
Precisely. The source mentions cardinality of a domain, D, which is just the number of values in it. The total number of possible tuples in the full Cartesian product is found by multiplying the cardinalities of all the domains together.
Okay. And the current relation state.
That just reflects the valid tuples that represent the real world right now. And of course, this state changes.
As data gets added, changed, deleted.
Exactly. A new customer signs up, an employee's address changes, the relation state updates to reflect that new reality.
The source also mentioned an alternative definition of a relation, something about order not mattering.
Yes, that's an insightful point. It suggests the order of values within a tuple isn't fundamentally important. You can think of the schema R as just a set of attributes, A1, A2, A.
A set, not an ordered list.
Right, and then a relation state R is a finite set of mappings. Each tuple is like a map. It maps each attribute name to a value from its domain. So a tuple becomes a set of attribute value pairs.
Like name Kumar, zip 223001.
Exactly. This view emphasizes the attribute name is what's key, not just its position in the row.
Interesting perspective. So to quickly recap the formal bits, RA1, Aeon, is the schema structure. RR is the state. Current data, which is a subset of the Cartesian product DUM A1X, X DEM and each tuple T in RR is like V1, Vn, where each Vi comes from DUM AI.
Perfect summary. And that little example they gave illustrates it well. Relation RA1, A2, domain 0, 1, and ABC. Cartesian product is all 6 pairs. A possible state could be just 0A, 0B, 1C. That's the table's content at that moment.
Okay. And the source helpfully maps the informal terms we use to the formal ones, right?
Yes, super useful for studying this.
Table relation.
Column header, S,
All possible column values, domain.
row, tuple.
Fill the definition, schema of a relation.
In a populated table, state of the relation.
Got it. That translation is key. Now, what about the characteristics of these relations?
Right, some fundamental properties. First, the source stresses. The order of tuples, rows, doesn't matter. Logically, it's a set. How they're displayed or stored might have an order, but the relational model itself doesn't rely on it.
So shuffling the rows doesn't change the relation itself.
Correct. However, it does note that in the basic definition, the order of attributes, columns, is considered ordered. But that alternative definition, using attribute value pairs, gets around that.
Okay, a subtle distinction there. What else?
Values must be atomic, indivisible. You can't store a list of phone numbers in a single cell, typically. Each cell holds one atomic value.
One value per cell.
And crucially, each value must be from the attributes defined domain. We keep coming back to that. Value in tuple T must be in nana.
Consistency is paramount.
Absolutely. And finally, the concept of the NUL value.
Ah, for missing data.
Exactly. It's a special marker used when a value is unknown, or maybe it just doesn't apply to that specific row. It represents missing or inapplicable information.
Not the same as 0 or an empty string.
Definitely not. It's a distinct state. The notation mentioned is also handy. T, or TAI, means the value of attribute AI in tuple T, and T, T, refers to a subpart of the tuple with just those specified attributes.
Okay, solid grasp on structure and characteristics. Now, how do we keep the data accurate? Integrity constraints.
Yes, relational integrity constraints. These are the rules that must hold true for any valid state of our relations. They enforce data consistency and accuracy.
The guardians of data quality?
You could say that. The source highlights 3 main types: key constraints, entity integrity constraints, and referential integrity constraints.
Plus that implicit domain constraint we already covered, values must be from the domain, or NOL if allowed.
Exactly. So let's start with key constraints. First up, superkey.
Superkey sounds powerful.
It is. For a relation R, a superkey, SK, is a set of one or more attributes where, in any valid state, no 2 different rows can have the exact same combination of values for those attributes in SK.
So the values in the superkey columns taken together must be unique for every row.
Correct. If you have 2 rows, their values for the superkey attributes must differ in at least one place.
Okay. And how does that relate to a regular key?
A key is a minimal superkey. It still guarantees uniqueness, but if they remove any attribute from it, it stops being a superkey. It's the smallest set of attributes that works for unique identification.
Ah, no redundant attributes in a key.
Precisely. The source uses a CR table example: state, reg tag, serial no, make, model, year.
Okay.
State, reg tag could be a key, unique within a state. Serial no is almost certainly a key on its own.
Right, serial numbers are unique.
Now consider serial no make. Is that a superkey? Yes, because serial no alone makes it unique. Is it a key? No.
Because make is extra, not needed for uniqueness.
Exactly. It's minimal. So every key is a superkey. Any set, including a key, is a superkey. A key is a minimal superkey.
Makes sense. And what's a primary key?
If a relation happens to have multiple sets of attributes that could serve as keys, these are called candidate keys, we choose one of them to be the primary key.
The main one.
The main one. It's often underlined in schema diagrams. And the CRR example would probably choose serial no as the primary key. It's the main identifier used for referencing this table from elsewhere.
And how do you choose?
Often you pick the smallest candidate key, fewest attributes, but it can sometimes depend on how the database will be used.
Got it. So keys ensure row uniqueness. What about the overall database schema?
Right. The source mentions the relational database schema as a whole. It's simply the set S of all the individual relation schemas, R1, R2, that belong to the same database.
Right.
Like the company database example would have schemas for employee, department, project, etc., all bundled together.
Okay, the collection of all table blueprints. Now, entity integrity.
This one's specifically about the primary key. The rule is simple. Primary key attributes cannot contain NLL values.
Never NNL in a primary key.
Never. Because the primary key uniquely identifies the row. If part of it could be NLL, that uniqueness guarantee breaks down. If the PK has multiple attributes, none of them can be NLL in any row.
Makes sense. Other columns can be NLL unless specified otherwise.
Yes, unless they have a specific not NLL constraint applied to them. Entity integrity is just for the primary key.
Okay. And the third main type, referential integrity.
This one is about relationships between tables. It involves two relations, a referencing relation, R1, and a reference relation, R2.
Okay.
In R1, you have one or more attributes that form a foreign key, FK. These FK attributes correspond directly to the primary key, PK attributes of R2.
So a column in one table points to the primary key in another table.
Exactly. We say a tuple T1 in R1 references a tuple T2 in R2 if the value in T1's foreign key column match the value in T2's primary key column. Schema diagrams usually show this with an arrow from R1.FK to R2.PK.
Like linking an employee record to their department record using a department ID.
Perfect example. And the core rule of referential integrity is this. The value in the foreign key column of the referencing table, R1, must either 1. Match an existing primary key value of the reference table, R2, or 2. Be NAL.
NALL is allowed.
NLL is allowed only if the foreign key attribute itself isn't part of R1's own primary key. This rule prevents dangling references having a record point to something that doesn't exist.
Ensures relationships are valid.
Exactly. And when drawing schemas, we underline primary keys and use those directed arcs to show foreign key relationships clearly. The source mentions the company's schema diagram shows this well.
Right. Beyond these core three, the source mentions semantic integrity constraints.
Yeah, briefly. These are more about application-specific business rules, things the basic relational model can't easily express.
Like
Like the example given. An employee cannot work more than 56 hours per week across all their projects. That's a complex rule involving calculations across multiple records.
okay. How are those enforced?
You usually need more advanced database features, like specific constraint languages, or SQL features called triggers or assertions, which can execute custom logic.
Got it. So we have the structure, the rules, now the actual data, the populated database state.
Right. At any time, each table has tuples, data. The overall database state is just the union of all those individual table states, and it changes constantly.
Through insert, delete, modify operations.
The basic updates. And importantly, these updates must not violate any of the integrity constraints we've discussed.
The constraints are always active.
Always. Sometimes one update might even trigger other updates automatically to maintain integrity. Like deleting a department might require updating employees who belong to it.
And if an update tries to violate a rule, what happens?
The system has options.
Yeah.
It might just reject the operation, restrict, or reject.
Stop it cold.
Yep. Or it might allow it but warn the user. Or it might trigger those automatic follow-up actions we mentioned, cascade or set null.
Cascade meaning?
If you delete a department, cascade might automatically delete all employees in that department, if the rule is set up that way. Set null might just set the department ID in the employee records to null.
Different strategies.
Right. Or the system could even run some custom error handling code defined by the user.
Let's think about violations per operation. Insert.
Inserting a new row could violate domain constraints, wrong data type, key constraints, duplicate primary key, referential integrity, foreign key doesn't point to existing primary key, or entity integrity, trying to insert NOL into a primary key column.
Lots of potential pitfalls. Delete.
Deleting a row mainly risks violating referential integrity. If other tables have foreign keys pointing to the primary key of the row you're deleting.
You would create dangling references.
Exactly. That's where restrict, stop the delete. Cascade, delete referencing rows too. Or set null, set referencing foreign keys to NL, come in.
Okay. And upate.
Updating a row could violate domain or not NLL constraints if you change a value incorrectly. But you could also violate key constraints if you change a primary key to one that already exists, or violate referential integrity if you update a foreign key to a non-existent value, or update a primary key that's being referenced elsewhere.
So constraints are checked constantly during updates.
They have to be. The source also includes that homework example, designing student, course, and role tables, etc. Drawing the schema diagram with foreign keys is a great way to cement these ideas.
Definitely good practice. Okay, structure and rules are down. How do we query this data? Relational algebra.
Yes, relational algebra. Our source introduces it as a procedural query language.
Procedural meaning step by step.
Exactly. You specify the sequence of operations needed to get the result. It takes relations, tables with data, as input.
And produces relations as output.
Always. The operators are either unary, one-input relation, or binary, two-input relations.
Yeah.
And it's recursive. The output of one operation can be the input for the next.
Building up complexity.
Right. A sequence of these operations forms a relational algebra expression, which represents our query. The final result is the answer, also in the form of a relation.
The source contrasts this with relational calculus.
Briefly, yeah. Calculus is non-procedural. You describe what result you want using logic, not how to get it step by step. But we're focusing on algebra here.
Okay, so the algebra operators. Unary ones first. Select and project.
Right. Let's break down select. Its job is to pick a subset of tuples, rows, from a relation based on a condition we specify.
Horizontal filtering.
Perfect way to put it. Keep the rows that match, discard the rest. Notation is condition. Sigma for select. The condition, the relation are.
Example, or salary 30,000 employee.
Exactly. Find employees in depth 4 or earning over 30K. The result has the same attributes, columns, as the original employee table.
And the condition.
It's a Boolean expression. Comparisons like NEO combined with AND or not. The system checks this condition for every single tuple. If true, the tuple is in the result.
So the result degree columns is the same, but the number of rows is less than or equal to the original.
Correct. The selectivity is just the fraction of rows to satisfy the condition.
And select is commutative. Order doesn't matter for multiple selects.
Right. As BA is the same as age, you can also combine cascaded selects using any A and BR.
Okay. Select filters rows. What about project?
Project works vertically. It picks specific columns, attributes, and throws away the others.
Vertical slicing.
Exactly. If you only want employee first name, last name, and salary, you use project. Notation. Attribute list R. Pi for project. The list of columns you want, the relation R.
Like a theme name, lame, salary, employee.
Perfect. The result is a new relation with only those columns in that listed order. The degree is just the number of attributes in your list.
Okay. Any touches with project?
Yes, a very important one. It automatically eliminates duplicate tuples in the result. Relations are sets, no duplicates allowed. If projecting causes identical rows, only one copy is kept.
Automatic deduplication.
Right. And unlike select, project is generally not commutative. Projecting on set A, then set B, might give a different result than projecting B, then A.
Good to know. So how do we combine these?
Usually queries need sequences of operations. You can nest them in one expression, like theme name, L name, salary, department 5 employee.
Select first, then project the result.
Right. Or you can use intermediate relations. Create a temp table, say DP5, EMPS, department 5 employee, do name, L name, salary, DEP5, EMPS.
Might be clearer for complex queries.
Can be. And if you use intermediates, you often need to name them. Which brings us to the rename operation. Symbol is row.
Renaming. Why?
To name intermediate results, or sometimes just to make expressions clearer or maybe prepare for operations like joins where attribute names need to match. You can rename the relation, the attributes, or both.
Like or SB1BN renames relation R to S and attributes A1 to B1BN.
Exactly. Or just you enter SR to rename only the relation. Or B1 BNR to rename only the attributes gives you flexibility.
Okay. Unary ops down, binary ops next. Union, intersection, minus.
Yes, the set operations. Big requirement here. The two relations must be union compatible or type compatible.
Meaning?
Two things. Same degree, same number of columns, and corresponding columns must have the same domain. Compatible data types.
Apples and apples, oranges and oranges.
Basically, yes, assuming they are compatible. Union, RS, gives all tuples in R, or S, or both. Duplicates removed.
Combines them.
Intersection, RS, gives only tuples present in both R and S.
The common ones.
And set difference, or minus, RS, gives tuples that are in R but not in S.
Subtraction.
Right. The source had that example. Find SSNs of employees in depth 5 or R who supervise someone in depth 5. You'd find each set of SSNs separately, likely involving joins for the supervisor part, and then union the two resulting relations.
Okay. Properties of these.
Union and intersection are commutative. Order doesn't matter, and associative grouping doesn't matter. Minus is not commutative. RS, ARS, R. And intersection can actually be built from union and minus, like RAS equals RRS.
Interesting. Okay, next binary op, Cartesian product.
Also called cross product or cross join. Unlike set ops, the relations don't need to be union compatible.
No compatibility needed.
Nope. If R has N attributes and S has M attributes, RS gives a new relation Q with N plus M attributes. All of R's followed by all of S's.
How many rows?
For every possible pair of tuples, one from R, one from S, you get a combined tuple in Q. So if R has NR rows and S has NS rows, RES has NR times MS rows. It can get big fast.
Every combination.
Every single one. The source mentioned finding dependents for female employees likely involves a Cartesian product of employee and dependent, then filtering, selecting, based on matching IDs and gender.
That filtering step seems key, which leads to join.
Exactly. Doing a Cartesian product, then immediately interest. Selecting based on a condition is so common, they may join a dedicated operation. It combines related tuples from two relations into longer tuples, essential for multi-table databases.
Like finding the manager name for each department.
Perfect example. You join department and employee, where department.mdr SSN, employee SNN, project the department name and manager name. Formally, R condition S is equivalent to Sucks condition, RAS.
So join and a Cartesian product plus select filter.
In essence, yes, the result has attributes from both R and S, but only includes the combined tuples that satisfy the join condition. It links related info.
Are there different types of join?
Yes. The general one is theta join, RSS. Theta is any comparison operator, or SAS, comparing an attribute from R with one from S, usually from compatible domains. Tuples with NL join attributes, or where the condition is false, are excluded.
Okay.
A very common type is equio join. That's a theta join using only the equals operator, like RAIBJS. The result will always have columns A and BJ with identical values in every row.
Makes sense. And natural join.
Natural join RS is special. It requires the attributes you're joining on to have the same name in both R and S. If not, you need rename first.
Same name required.
Right. Then it does an equijoin on all attributes that share the same name. But here's the twist. It only keeps one copy of each common attribute in the result, not duplicates like equijoins.
Tidies up the result.
Exactly. The join condition is implicitly the ND of equalities for all matching attribute names. If no tuples satisfy the condition, the result is empty.
The source also mentions SQL join types.
Just briefly, for context, inner join basically covers theta, equi, and natural joins. Outer join, left, right, full, is different. It keeps all rows from one or both tables even if there's no match, using NLs to fill the gaps. Ensures no data is lost just because it lacked a match.
Okay, different purpose. One more algebra operation, division.
Division. This one's a bit more niche. RES finds tuples in R that are related to every single tuple in S based on common attributes.
Every single one.
Yeah, the classic example. Find employees who work on all projects that John Smith works on. You'd find Smith's projects, relation S, then divide the employee project, relation R, by S.
Finds those who match everything in S. Tricky.
It can be. Usually involves several steps to set up R and S correctly.
The source then listed more query examples using these operations, right?
Yeah, like finding employees in research, or project details for projects in Stafford, or projects involving Smith as worker or manager. Shows how you combine select, project, join, union, etc. to answer real questions.
Okay, that's a solid tour of relational algebra. Powerful stuff. Now, how does this translate to the real world? SQL.
Exactly. Structured query language.
Yeah.
SQL. It's the standard. Our source notes it has DDL, data definition language, DML, data manipulation language, and DCL, data control language.
Definition, manipulation, control.
Right. DDL defines the structure. DML works with the data. DCL handles permissions. SQL can be used standalone or embedded in other languages.
And it's declarative, not procedural like algebra.
Mostly, yes. You describe the result you want, not the steps to get it. It's based on the relational model, though implementations aren't always perfectly pure. And you can map ER designs directly to SQL. Entities become tables, attributes become columns, relationships use foreign keys, sometimes needing extra tables for many-to-many.
So relation, SQL table, attribute area, SQL column. Got it. What about schemas and catalogs in SQL?
Good question. And SQL schema is a named collection of database objects, tables, constraints, views, etc., usually owned by a user. You create it with create schema.
A container for related objects.
Pretty much. And SQL environment is just the installed RDBMS software. A catalog is a collection of schemas. Every catalog has a special information schema, which describes everything else in the catalog.
Like metadata.
Exactly. And an important point. Integrity constraints between tables usually require them to be in the same catalog. Schemas in the same catalog can share things, though.
Okay, let's revisit DDL and DML.
DDL defines the conceptual schema. Create table, alter table, drop table are key DDL commands. DML manipulates the data. Select, insert, update, delete are core DML commands.
So DDL builds the house, DML furnishes it, and rearranges the furniture.
Nice analogy. SQL data definition, DDL, specifies the tables, their columns, name, data type, constraints, primary key, foreign key, not NL checks. Indexes for performance, security, storage, details the whole blueprint.
And the main command is create table.
Absolutely. Create table lets you name the table, define attributes, name, data type, and specify constraints like not NL right there. Tables made this way are base tables physically stored.
Like create table department, dname varchar 15, not null, dnumber integer not null, mgrsn charna.
Perfect. SQL 2 and later versions enhanced create table to let you explicitly define primary key, unique, for secondary keys, and foreign key constraints within the command too. Makes defining the structure and rules much cleaner.
And data types. We need to choose those carefully.
Very carefully. SQL offers standard types: numeric, integer, float, decimal, character strings, char for fixed length, varchar for variable, bit strings, Boolean, date time types, date, time, stamps, and stamp. The type dictates what values are allowed and how they're stored.
Okay. What about specifying other constraints in SQL?
Lots of options. At the attribute level, not null, default.
Yeah.
Value to use if none provided. Check.
Yeah.
Value must satisfy a condition.
Like check age 0.
Exactly. At the table level, primary key, one or more attributes. Unique, alternate key allows nulls usually. Foreign key references in other tables PK.
And the foreign key can have actions.
Right. On delete or on update actions like set null, cascade, set default, tells the database what to do if the reference primary key changes or gets deleted. You can also name constraints using constraint name, which helps if you need to modify or drop them later. And table-level check constraints can involve multiple attributes.
Lots of control over data integrity. What if we need to get rid of a table?
That's drop table. The source warns.
Yeah.
Use with extreme caution. It deletes the table definition, all its data, indexes, constraints, everything. It's usually irreversible. Date gone forever.
Ouch. Okay. What if we just need to change a table?
That's alter table. It modifies an existing table structure. You can add columns, delete columns, change a column's data type if possible, add or drop constraints, not null, unique, check, primary key, foreign key. Very versatile for evolving database schemas.
Adds flexibility after creation. Okay, DDL covered. How about DML? Getting data in. Insert.
Insert adds new rows, tuples. You specify the table name, you list values in the order the columns were defined, or explicitly list column names and then the corresponding values. Good if sipping columns with defaults or NLs.
Got to provide values for not NL columns without defaults, right?
Absolutely. Some systems let you insert multiple rows at once, and there's create table, as select creates a table and populates it directly from a query result. Very efficient.
Okay. Removing data. Delete.
Delete removes entire rows based on a where clause condition. Very important. Delete operates on one table at a time. But referential actions, cascade, set null, might trigger deletion updates in other tables.
What if there's no where clause?
Delete without where deletes all rows. Empties the table, but the table structure remains. Use drop table to remove the structure too. There's also truncate table, which also deletes all data, often faster than delete, but works slightly differently. IG might reset identity counters.
Got it. And modifying existing data. Update.
Update modifies attribute values in existing rows, again using a where clause to select which rows.
Yeah.
The set clause specifies which attribute to change and their new value. You can set to unnull or default if allowed.
And updating primary or foreign keys can trigger those referential actions.
Yes, if they're defined. Like delete, update works on one table per command.
Phew. That covers a huge amount of ground.
It really does.
Yeah.
So just to wrap up the core ideas, we looked at the relational model domains, tuples, attributes, keys, relations, then schema and state, and those vital integrity constraints. Key, entity, referential.
Then we jumped into relational algebra select, project, the set operations, Cartesian product, and all of those joins, the procedural way to query.
And finally, we hit SQL. DDL for structure, create, alter, drop, and DML for data manipulation, insert, delete, update.
Absolutely essential foundations for anyone dealing with relational databases. Understanding this stuff is crucial for design, querying, everything.
Definitely. And as we said, this is really just scratching the surface. We could dive deeper into advanced algebra, complex SQL queries, normalization theory, transaction management. Lots more ground to cover in the future, perhaps.
For sure. And for our listeners, as you see data around you, spreadsheets, apps, lists, try thinking about how it might be structured using these relational concepts we talked about today.
It's a great exercise. And a final thought to leave you with. Consider how critical those integrity constraints are. What would happen to data reliability if key constraints, entity integrity, or referential integrity were just ignored or badly implemented? It really highlights why careful design matters so much.
A very important point. Well, thank you for joining us on this deep dive into the fundamentals of relational databases.